acid-base reaction involves the transfer of a proton from an acid to a base. So let's take a look at the mechanism for proton transfer. Mechanism attempts to show how starting materials are converted into products during a reaction. And we use energy diagram to talk about how the changes in the potential energy goes as reactants proceed to product in a chemical reaction. So let's take a look at our acid-base reaction first. So suppose we dissolve hydrogen bromide in water. As we know, hydrogen bromide, HBr, is an acid. It's going to dissociate to give proton and Br. And the proton will combine with water molecule to form hydronium ion. So what happens is the water serves as the base to grab the proton, and HBr bond breaks and Br leaves. Alright, so the product is the hydronium ion and the bromide ion. Water is the base, so the hydronium is the conjugate acid. HBr is the acid, and the Br minus is the conjugate base. So that's our acid-base reaction. All right, we have the reactants and the products. So now let's take a look at the energy diagram. In the energy diagram, the vertical axis is the potential energy. The horizontal axis will be the reaction coordinator, or you can think of it as the time. So as time goes by, reactant starts to react with each other and gives the product. All right. So here is our starting point. We have our reactants, and in this reaction, H2O and HBr. And on the other side of the curve, our products, and in this reaction, the hydronium ion and the bromide ion. All right. So we are going up a hill as we start the reaction. The energy difference between the starting point and the top of the hill is our activation energy. We use EACT to represent it. Okay, it's called the activation energy. Every chemical reaction has a certain minimum increase in potential energy necessary for the process to occur. This is a thermal energy, and mainly it's overcome by collision of the molecules. Okay, so that's the activation energy that we need to overcome in order for the reaction to take place. And we also have an energy difference between the reactant and the product. We use delta G to represent it. And I'm sure you have learned about this from general chemistry. Delta G is the Gibbs free energy. It's the energy that is required for the overall reaction. For this particular case, the product has lower energy than the starting material. So delta G will be a negative value, and the reaction will be an exothermic reaction. Okay, the reaction will give off energy as the product is formed because the energy of the product is lower. Alright, now on top of the hill, we have our transition state. Transition state is the point of the maximum potential energy encountered by the reactants as they proceed to the product. You need to keep in mind that transition states are not stable. They cannot be isolated or examined directly. And at the transition state, the bond forming and the bond breaking take place at the same time. So here is the structure of the transition state of this acid-base reaction. We have dotted line between oxygen and hydrogen showing that a bond is forming between the oxygen and hydrogen. The dotted line between hydrogen and bromine showing that the bond is breaking between HBr. Okay, so we have those partial bonds, and as a result, there is a partial negative charge forming on bromine and a partial positive charge forming on the oxygen. So what we just described is one elementary step. Elementary step is one that involves only one transition state. It's one concerted reaction that involves bond forming, bond breaking taking place at the same time. Okay? So let me redraw the transition state of this reaction. OH bond is forming and HBr bond is breaking. The bromine start to have the negative charge and the oxygen started to have the positive charge. So both of them have the partial charges. And for transition state, typically we use a square bracket to put it in a square bracket and put this little sign, an equal sign, an unequal sign on the top right corner to show that this structure is a transition state. Okay, so basically when we are talking about one elementary step, there is only one transition state and there is only one hill in the energy diagram. I'm going to briefly talk about the intermediate. The intermediate is formed in one elementary step and consumed in another. Intermediate is not the initial reactant nor the final product, but it lies in the pathway from the reactant to the product. So what that means is, if a reaction has more than one elementary step, we will have two hills, and there will be a valley between those two hills, and that valley will represent an intermediate. Okay, so here is what we're talking about. On the left side, that's our reactant. On the right side, that's our product. Here we have two hills. Those are the transition state 1 and transition state 2. The valley between those two hills will be an intermediate. Okay, so intermediate is formed in one elementary step and it's consumed in the next step. And typically, intermediate is not isolated either, even though it might be more stable than the transition state. We will see reactions with different types of intermediates later in the next chapter. So just to let you know, we may have some of these new terms coming up. Alright, so the concept of molecularity. Molecularity is the number of species that undergo a chemical reaction, a chemical change in that step, in that elementary step. If the elementary step involves two molecules, we say that's a bimolecular reaction. If it involves only one molecule, we call it a unimolecular reaction. So the bi means two, uni means one. So these two types of reactions will cover pretty much all the chemical reaction steps. It will be very rare for three molecules to collide at the same place at the same time. All right, so most cases either bimolecular or unimolecular reaction. The proton transfer reaction that we just covered, it involves the base grab the proton from the acid. So this is a bimolecular reaction. It involves two molecules in the elementary step, the acid and the base. Generally speaking, the proton transfer is a very fast reaction, so the activation energy is relatively low and the reaction will be an exothermic reaction, which means the product is more stable than the starting material. All right.